Hi everyone, my name is Christof Torres. I'm a PhD student at the University of Luxembourg, and today I will be presenting a work called ConFuzzius, a data dependency-aware hybrid fuzzer for smart contracts. This is joint work with my colleagues Antonio Iannillo, Artur Gervais, and Radu. As some of you probably already know, in the past few years, smart contracts have been victims to a number of attacks. The most prominent attacks are probably the DAO attack that occurred in 2016 and the two parity wall attacks that happened in 2017. However, almost every year there's at least one or two reportings about smart contracts being hacked and resulting in millions of dollars being stolen. Thus, creating tools that can help developers to automatically detect bugs is therefore of utter importance. Now, there are three main challenges that tools need to solve when analyzing the security of smart contracts. The first one is the statefulness of smart contracts. We solve this challenge by creating sequences of transactions that exploit read after write dependencies that are retrieved while fuzzing. The second challenge is input generation. We solve this challenge by leveraging symbolic execution to generate inputs that help our fuzzer getting past complex path conditions. The third challenge are environmental dependencies. We solve this final challenge by modeling environmental information such as block timestamps or return values of contract calls as fuzzable inputs. We'll now briefly present the architecture of ConFuzzius and highlight some of its main components. ConFuzzius consists of an evolutionary fuzzing engine that follows a simple genetic algorithm. ConFuzzius takes as input a smart contract and an optional blockchain state, which are both first fed into the evolutionary fuzzing engine, which then creates a population of individuals by following a genetic algorithm. Each generated individual is then executed using an instrumented Ethereum virtual machine, which then produces an execution trace. The execution trace is afterwards analyzed by the execution trace analyzer in order to generate new inputs, measure code coverage, detect bugs, and perform data dependency analysis. This creates a feedback loop, and the entire process is repeated until a termination condition is met. At the end, ConFuzzius produces a report containing statistics such as code coverage and which individuals triggered which bugs. As in any genetic algorithm, the encoding of individuals is crucial. Here you can see that an individual consists of a sequence of what we call inputs. Each input consists of an environmental part containing, for example, the current block timestamp or block number, and a transaction part containing, for example, transaction value or the function parameters. Now, another important aspect of our fuzzer is the capability to combine transactions in a meaningful way by leveraging data dependencies across individual transactions. Our fuzzer infers access to state variables dynamically during execution by observing access to storage instructions as load and as store. Our goal is to retrieve the access to a variable and not necessarily the exact storage location. We differentiate between statically sized and dynamically sized variables. Statically sized variables include primitives such as integers and booleans, but also structs and fixed arrays. Here the storage variable is simply the exact storage location, which is retrieved by simply popping the first element from the stack. Dynamically sized variables are more challenging since we cannot invert hash functions. However, for mappings, for example, we can keep track of the SHA-free hash results and the memory contents that were used to create the hash. To deal with concatenation, we only extract the last 32 bytes from the memory contents. Those 32 bytes represent the location of the storage variable. Finally, for dynamic arrays, we also keep track of the arithmetic additions of SHA-free hashes in order to later infer the storage variable. We will now present the evaluation of our fuzzer. We ran our experiments using two different datasets. The first dataset consists of a real-world dataset of over 21,000 contracts with source code that have been retrieved from Etherscan. We clustered them using k-means into a large cluster and a small cluster, where the small one consists of contracts with less than 3,632 instructions, and the large cluster consists of everything else. The second dataset is based on the SmartBugs curated dataset, which we extended with 5 additional types from the SWC registry. We end up having 128 contracts with 148 annotated bugs across 10 different types of bugs. As baselines for our comparison, we chose 3 symbolic execution tools, namely Oyente, Imperial, and Imperial Pro, as well as 2 fuzzers, namely ILF and SFuzz. Finally, we run each of our experiments using 10 runs with independent seeds, providing 10 minutes of execution time for small contracts and 1 hour for large contracts. Now, the first research question that we wanted to answer was whether ConFuzzius achieves a higher code coverage than current state-of-the-art smart contract symbolic execution tools and fuzzers. We used a real-world dataset to measure code coverage due to its diversity in terms of size and number of contracts. In this figure, you can see that ConFuzzius achieves on average the highest code coverage for both small and large contracts. For small contracts, our fuzzer achieves 91%, and for large contracts, it achieves on average 81%. As expected, all the tools struggle more with the large contracts. However, while ConFuzzius only has a difference of 10% between small and large contracts, other tools, such as Ferreira, for example, have a difference of 31% between small and large contracts. Now, if you compare the three fuzzers in terms of code coverage over time, we see that ConFuzzius outperforms ILF and SFuzz. Our fuzzer achieves already after 1 second 66% code coverage on average on the small contracts, while ILF and SFuzz only achieve 12% and 15% respectively. In terms of large contracts, ConFuzzius achieves on average 46% code coverage already after 1 second, while ILF and SFuzz only achieve 10% and 11% respectively. The second research question tries to answer the question whether ConFuzzius discovers more bugs than current state-of-the-art symbolic execution tools and fuzzers for smart contracts. We therefore run ConFuzzius and the other tools on a curated dataset with annotated bugs. We see from the table that ConFuzzius detected more bugs than the other tools with 106 out of 148 bugs. We also see one of the benefits of fuzzers. All the symbolic execution tools reported false positives. ConFuzzius, however, did not report any false positives. Despite being fuzzers, ILF and SFuzz reported some false positives for bugs of the type unsafe delegate call. After further inspection of their code, we found out that it's due to the implementation of their detectors. Both tools report an unsafe delegate call if the data of a delegate call can be passed as a function argument. However, this is not sufficient. As you can see from the short code snippet, the destination of the delegate call is only settable by the owner and therefore it is safe. Now, our last and third research question is to understand how relevant ConFuzzius individual components are in terms of code coverage and bug detection. We therefore randomly selected 100 contracts from each cluster of the real-world dataset and disabled each component separately. We see from our results that each component is an added value. We also see that constraint solving plays an essential part in achieving code coverage and vulnerability detection. Moreover, environmental instrumentation is more relevant for detecting bugs than for achieving code coverage. Finally, we see that data dependency analysis allows to find 10% and 18% more bugs in small and large contracts respectively. Now we'll shortly conclude our work. We presented ConFuzzius, the first data dependency-aware hybrid fuzzer for smart contracts that is capable of tackling the following three challenges: input generation by combining evolutionary fuzzing with constraint solving, then stateful exploration by leveraging read-after-write access patterns across state variables, and finally environmental dependencies by modeling block and contract information as fuzzable inputs. We also compared ConFuzzius against 2 state-of-the-art fuzzers and 3 symbolic execution tools using 2 datasets: a curated dataset of 128 contracts and a dataset of over 21,000 real-world contracts. ConFuzzius was able to detect up to 23% more bugs and achieved up to 69% more code coverage than the compared tools. We also showed that data dependency analysis can help boost the detection of bugs up to 18%. These are just a few of our results. Please check out our paper for more details, even more results. I would like to thank you for your attention. Moreover, all the code and data is publicly available on GitHub. If you have any questions, feel free to drop me a message at christof.torres@uni.lu. This work was supported by the Luxembourg National Research Fund and the Horizon 2020 program by the European Union.